Okay, we are now ready to generalize our understanding of transmission lines with AC signals toward arbitrary loads or any combination of resistors, capacitors, and inductors at the end of a transmission line. All right, so let me just start by recounting the equation for input impedance. And so the scenario that we have in mind is a transmission line . The transmission line has intrinsic impedance of Z0, which just defines the ratio of voltage to current for any traveling wave along the transmission line. And at the end of this transmission line is a load that we characterize with an impedance Z sub L. Z sub L could be a combination of resistors or capacitors or inductors. ZL will have potentially both a real and imaginary parts. Right, so ZL could be equal to A plus J times B, where A would be the resistor or the resistive part of it, and B would be the reactive part of it. And B can also be subdivided into two categories. A positive reactive negative component means it's inductive, and a negative reactive component means it's capacitive. We're calling that the equivalent impedance of a capacitor is negative J over omega C, and the equivalent impedance of an inductor equals J omega times L, the inductance. So whatever is the value of the imaginary part of the inductance, you can basically convert that back and forth to an equivalent capacitor or an equivalent inductor, depending on whether it's positive or negative. All right, so ZL is a complex number in general. It could have a real imaginary part. And we have covered the situation where ZL is an open circuit, where it's infinite. We have covered the situation where ZL is a short circuit, where it's equal to 0. And we've also covered the situation where it is a purely an inductor or capacitor, where only the imaginary part is there. And we've covered the case where ZL is purely resistive, where A is equal to something other than 0 and B equals 0. So whatever ZL is, the equation for the input impedance looks like this. Zn equals Z0 times ZL plus J Z0 tangent of beta D divided by Z0 plus J ZL tangent of beta D, where D is the length of the transmission line. Beta is 2 pi divided by the wavelength. The frequency times the wavelength equals the propagation velocity. And the input impedance is basically defined at the input at distance d away. Right, so what input impedance means, just to remind you, is that if you just had a wall that had 2 terminals in it, you had no idea what was on the other side of the wall. But you had the ability to place a voltmeter between those 2 terminals and then measure the current that appears. And if you convert each of the voltage and the current into phasors, and you take the ratio of the voltage to the current, that ratio will be equal to Zn. And because the transmission line forces the relationship between the output or the reflected current, defines a relationship between the reflected current that comes back to you and the current that you put in, the total current has to be the sum of the two. And so Zn can also be written as Vin plus V out as phasors divided by I in plus I out. All right, so this is the definition of the input impedance. And it's important to note that it is a function of distance, meaning if you instead measure the input impedance here, let's call this ZNB, you would measure a different value, right? Where this value here is, some distance x. Then Zn measured at this distance x away from the load will be something different because this beta d is different. Beta d can be thought of as the length of the transmission line in radians, right? So it's basically comparing it to the wavelength, but then multiplying it by 2 pi. All right. So let's consider for a second what happens if Zn is complex. So if Zn is complex, what that basically tells us is that the total voltage and the total phase are out of phase with each other, right? And the angle of Zn defines the phase shift between the total voltage and the total current. Right, so the angle of Zn defines a phase between the total current and the total voltage. Whereas the absolute value of Zn defines the ratio of the total voltage to the total current. All right, and just to make this clear, the I in plus I out is what I'm referring to when I say total current, and the V in plus V out is what I'm referring to when I say total voltage, right there. All right. So let's consider this for a couple of different scenarios. All right, so we have covered the case where we just have a pure resistor, where we have a transmission line terminating in a resistor. I'm going to put some numbers to this. Let's say we have an intrinsic impedance of 100 ohms and a load of 50 ohms. All right, if that's the case, then we can sort of observe what's going to happen from the reflection coefficient here, right? The reflection coefficient at the load equals RL minus C0 over RL plus C0. Let's actually generalize this now. Instead of RL, let's put ZL, since this same equation applies even if the load is a capacitor or an inductor. So let's make this a ZL, and this works out to be 1/3. All right, so let's consider I have a positive going wave right here. Right, here's Vn. It's moving this way. At this point right here, the voltage phasor will be equal to, let's say it equals to cosine of omega t. Right, let's actually not make this a phasor. Let's keep this in a time domain for once. All right, so the voltage just as it reaches the load is cosine of omega t. Right after the reflection, we're going to have a voltage of 1/3 of cosine of omega t. All right, so the basic concept of reflection at the load still applies. But let's now consider the same scenario, except we've got a reactance on the load. All right, so here is the same transmission line. All right, same 100 ohms on that transmission line. And let's say we have a capacitor on the load for which ZL equals minus J times 50 ohms. All right, we can figure out what that reflection coefficient at the load is in the same manner as before. Gamma L equals ZL minus C0 over ZL plus C0. And this works out to be negative J. All right, so what does it mean for the reflection coefficient at the load to be a complex number or an imaginary number? okay? What it tells us is that the ratio of voltage to current of what comes into the load and what reflects is going to be the magnitude of gamma L. So if, let's again consider this, right? If this is V positive, it's entering the load. If V positive is again that cosine of omega t, then the voltage right after it reflects the load from the load will be equal to, first of all, we're going to write down a cosine. All right, now the magnitude of this reflection coefficient is 1. So we're not going to scale this amplitude here, this 1 right here. We're not going to scale that at all. But we are, however, going to change the phase. In fact, we're going to subtract 90 degrees of phase from the reflected wave. So this is going to be omega t minus pi over 2. Pi over 2 being 90 degrees of a phase shift, except in units of radians, right? We generally want to keep this to radians. All right, so we can deal with arbitrary loads, and we can calculate reflection coefficients with complex numbers. And all we're doing is we're capturing the amplitude of what reflects and how the phase changes with that reflection as well. So we can extend this to arbitrary loads, and everything is still going to work. So let's say we've got the same 100 ohm line, or let's say actually we've got a 50 ohm line, and it ends in a capacitor inductor series. The capacitor is 50 ohms, and the inductor is J times 50 ohms, in which case ZL will just be the sum of the two since they're in series. So ZL will equal 50 plus J times 50. All this is in ohms. All right, we can again calculate what the reflection coefficient is. It's ZL minus Z0 times ZL plus Z0. I'm talking specifically about the reflection coefficient at the load. And this works out to be, if you plug in the numbers, 0.447 at an angle of 1.11 radians. Or you can put it as a real and imaginary number. It works out to be 0.2 plus J 0.4. That is the reflection coefficient. All right. If that's the case, let's repeat the exercise here. The voltage that is approaching the transmission line, moving in the positive direction, if it is cosine of omega t, then the voltage right after reflection going in the negative direction will be equal to 0.447, right? We have to shift the amplitude, times cosine of omega t plus 1.11, where that number is in radians. All right. So that should hopefully broaden our understanding of what impedance means and how it relates to reflections at the load. And so the takeaway from this is that we can treat everything the same way if we have complex numbers. We just have to keep everything in complex numbers. We can still calculate reflection coefficients. We can still calculate impedances. All we got to do is maintain everything in complex numbers and just interpret things correctly. All right, so given that, and given this equation right here of input impedance as a function of the load, as a function of the length of the line, let's try to understand graphically what's going on here, right? And so what we're going to have is basically a repeating cycle, just like we had before. We're at the quarter wavelength point, we sort of get a flipping of everything upside down, and at the half wavelength point, you're back where you started. All right, so I'm going to draw this little cycle with 4 little quadrants. This is going to be inductive impedance. Right. Over here, This is going to be the max resistance. All right, this bottom box right here will be capacitive impedance. And this box over on the left is minimum resistance. All right, so this basically is a cycle, a circle, or a loop that as you lengthen or shorten the transmission line, you're spinning around this circle. Each time you change the length of the transmission line by a half a wavelength, you're making one revolution around this circle. All right, so if you increase the length of the transmission line, you'll be moving in the clockwise direction. If you decrease the length of the line, you'll be moving in the counterclockwise direction. All right, so this is decreasing D. We'll go that way. Okay. Now, let's say that you have a situation where your Z let's talk about how ZL compares to Z0. That's going to be the key. All right, so let's start with the scenario where ZL, where the real part of ZL is greater than Z0. Right? You've got more you've got more real resistance in your load than you've got impedance in your line. If that's the case, then you want to start on the right half. Right? Because we're sort of starting out at D equals 0 at the load. We've got a bigger load resistance than we have line impedance. So we're going to start to the right of this plot, somewhere to the right toward the max resistance branch. On the other hand, if the real part of ZL is less than the line impedance, then you're going to start on, shockingly, the left half. Right? Because you're sort of seeding this at D equals 0 with a smaller resistance on your load than you have impedance in your line. All right, so that's two conditions right there. Let's also talk about the imaginary part of our load impedance. Okay, if the imaginary part of ZL is greater than 0, we have a positive imaginary part on our load. That implies we have an inductive portion, and so you're going to start in the top half of this chart. Right? Because you're starting out in inductive, and then as you sort of add transmission line between you and the load, then you're going to sort of move in the clockwise direction. The flip is also true if the imaginary part of ZL is less than 0, then you start in the bottom half. So based on how ZL compares to Z0, you know where to start on this loop, and then as the line gets shorter or longer, you either move clockwise or counterclockwise as you add or subtract transmission lines. All right, so you can see from this perspective that there ought to be a graphical representation of all of this, right? Something that can sort of capture these loops, these circles, depending on how ZL compares to Z0. So we're going to get that in a second. It's called a Smith chart. But before I show that to you, I want to take a look at this with the visual demo. And I'm actually going to open not one, but two copies of WinTLS side by side. All right. So in both of these, I'm going to set the source to be a sine wave. And the load I'm going to set to be impedance. That lets us sort of arbitrarily fix what the load impedance is. All right, in this left window, I'm going to set the imaginary value, the imaginary component of the impedance, to be 50 ohms. And in this one, I'm going to make it be negative 50 ohms. Right, so this left one basically has some inductance to it, and the right one has some capacitance to it. They both also have a 50 ohm impedance to it. All right, I'm going to now run the simulations in both windows. I'm going to wait for that to settle out. Speed things up. All right. For both lines, however, what I want to note is that the resistive part of the load matches the impedance of the line, right? So if you just looked at the resistor, you'd say, hey, 50 ohms is the perfect match. Unfortunately, there's also the reactive portions that are going to contribute, right? So even though you've got the resistance of the load matching the impedance of the line, this clearly is not a perfect match. If you take a look at these results here, this has an element of a standing wave to it. Yes, there is motion. Yes, there is some propagation of the wave, but there's also that bouncing up and down action, which we associated with the standing wave, or the positive and negative crisscrossing waves that basically cancel each other out. There's a mix of those two things. All right. I want to click on the envelope button in both of these simulations so you can sort of see. If we trace out this envelope, that's basically the intensity of the voltage phasor measured at that point, right? And it varies as a function of distance. That's the interference pattern of the outgoing and returning wave that echo on top of each other. The reflected wave is not as big as the wave that's going toward the load, but it's enough to create this, this interference pattern there. All right. Now, what you'll notice if I compare these two situations, that the standing wave pattern of these two appear to be the same, right? The standing wave ratio is identical. If I look at the ratio of the maximum voltage to the minimum voltage, it appears to be the same in both of those, right? So they both have the same standing wave ratio. But the one thing that's different is where you are in the cycle, right? Where in the right one, in the left one, where you had the inductive component to ZL, you're starting out closer to the maximum of the voltage. In this case, where you have a capacitor along with the resistor, you're starting out closer to the minimum, right? So the only difference between these two scenarios is basically where you start out in this cycle, right? This circular cycle right here. Let me move this over here. You can put these side by side. So in this left-hand example, where we have a positive imaginary portion, we're going to start out on the positive side, the upper half of this loop. But because the 50 ohm matches the 50 ohms, we're probably somewhere over here to the right. All right, so let me try something else. I'm going to, in one of these, I'm going to replace the resistor with the value 70.7 ohms. All right, I'm going to rerun the simulation, and let's see how this works. All right, I'm picking 70.7, by the way, because that equals 50 times the square root of 2. All right. All right. Hang on. All right, so I'm also going to get rid of this capacitor right here, and we're going to simulate this. Let that settle out. So this now is just a resistor. There is no more capacitor on the load. So let's let that settle out. And once it does, I'll click this envelope button, and you'll see that right there. All right, now, if I were to ask you the question, which one of these do you think is a better match, you might have been inclined to suggest the one on the left, because that's got the 50 ohm resistor, which matches the impedance of the line. On the right, we've got a load resistor of 70.7 ohms, which clearly is different from 50. Yet you can clearly see that the standing wave pattern on the right is smaller. In other words, this is actually a better match. You have more energy that's going toward the load and less energy that's reflecting and coming back. So you have to look at the combination of the resistance and the reactance in order to actually characterize what is happening. And you can see this if we figure out what the reflection coefficient is. And it works out to be, if the load resistance is 50 plus J50, that implies that the absolute value of the reflection coefficient is 0.447, right? Since Z0 equals 50 ohms. In the other case, where ZL equals 50 minus J50, that gave us an absolute value of the reflection coefficient of 0.447. That's a 7 right there. So we have the same reflection coefficient in both those cases. The sign is different, but the reflection coefficient magnitude is the same. Therefore, these two have the same voltage standing wave ratio, or Viswar. All right. If ZL is strictly a 70.7 ohm resistor and no capacitance and no inductance, that works out to have a reflection coefficient magnitude of 0.17. And so this will be a smaller Viswar. All right. So with that, given this sort of graphical structure, right, you take a look at how the load impedance compares to the line impedance, you figure out where to start on the circle, and then you basically slide around the circle as you pick points up and down the transmission line. There is a more common graphical representation of this called a Smith chart. So let me show you that Smith chart. This is a very famous diagram invented by someone named Philip Smith in the 1930s, was at Bell Labs, and he came up with this to sort of very quickly solve transmission line equations. And what you'll see is that there's a lot of markings on this, and believe it or not, it's still very often, even these days with fast computers, it's often faster to use a Smith chart than it is to whip out some calculator and plug it into the ZN formula. And so you can take a look at this label right here. This is wavelengths toward generator. All right, so if I know what the impedance is at a certain point, and then I sort of slide my measurement toward the generator or away from the load, then we're moving in this clockwise direction. All right, here you can see this is labeled wavelengths toward load. And so as we move our sensing point away from the load, or sorry, toward the load, we're going to go in this direction, or the counterclockwise direction. All right. The rest of these labels, let me kind of demonstrate this in the next slide. So the horizontal axis of this is the real part of your load impedance divided by your line impedance, right? So just take whatever that ratio is. You're basically normalizing your line to your load, and take the real part of that, and that's what's going to appear on the horizontal axis. So in this case, this point right here, 1.0, that would imply the condition where if you normalize ZL divided by Z0, the real part of that equals 1. So that's the beginnings of a match. The vertical axis is the imaginary part of that normalized line impedance. All right, so you can see that as well. Again, 1.0 is basically where things are a perfect match. And you go up or down as the imaginary portion of the normalized line impedance is. All right, so these circles basically represent paths which have the same real part of your input impedance. So as you sort of slide around the transmission line, or lengthen the transmission line and shorten the transmission line, you're basically spinning around this circle exactly as we described earlier. All right, the arcs here are paths of constant imaginary components of Zn. All right, so as you lengthen the transmission line, you're going to just keep walking in the clockwise direction. Now, these different circles here basically are going to refer to different scenarios. So in the case where you have a perfect match, you'll basically be sliding along this circle right here. Right, where you sort of start out with a perfect match right here. Then you'll be sort of walking around in this circular pattern. And then as the real part of this normalized impedance changes from 1 to 3, the circles get smaller and smaller. As the real part of the normalized impedance goes to 0, the circles get bigger and bigger. Right? And so you can basically read off from this chart what exactly is the angle of the reflection coefficient just by seeing where you are along this circle. Right? This is angle here in degrees, 80 degrees, 70 degrees, 60 degrees. And you've also got the magnitude of the reflection coefficient labeled here as well. Right? So all the information that you need is captured in this Smith chart. All right, so that's going to conclude this video here, where we can sort of see qualitatively and quantitatively how the input impedance varies as a function of transmission line length and as a function of what your load impedance is. And so in the last part, we're going to consider impedance matching, or how we actually design transmission lines to minimize reflections back to your source.